What specific problem does TULIP aim to solve in contrastive image text, CIT, learning, and how does it address the limitations of existing models like CLIP and SigLIP?
TULIP aims to solve the problem of inadequate representation of detailed spatial information and nuanced visual details in existing contrastive image text, CIT models like CLIP and SigLIP. These models often excel in high-level semantic tasks, but struggle with fine-grained visual understanding and spatial reasoning due to a lack of focus on precise spatial understanding and detailed annotations. TULIP addresses these limitations by incorporating patch-level global and local multi-crop augmentations, a reconstruction objective to preserve high-frequency local visual details, and a generative data augmentation strategy called JCO, which generates challenging hard negatives for improved semantic grounding. As a result, TULIP enhances performance across various downstream tasks, including zero-shot classification and visual question answering, while maintaining the language grounding strengths of existing CIT methods. Ultimately, TULIP demonstrates superior performance in both vision-centric and language-centric tasks, significantly outperforming existing models.
How does the proposed TULIP method work? Illustrate its methodology step by step, focusing on the different components such as global, local multi-crop augmentations, reconstruction objectives, and generative data augmentation.
The proposed TULIP method enhances contrastive image text learning by integrating several innovative components. First, it employs global and local multi-crop augmentations to capture detailed spatial information, allowing the model to learn from both broad and fine-grained visual features. Second, TULIP introduces a reconstruction objective that encourages the model to retain high-frequency local visual details, ensuring that it can reconstruct images accurately from latent representations. This is achieved through a masked autoencoder for images and a causal decoder for text, balancing semantic invariance with visual fidelity. Lastly, TULIP incorporates a generative data augmentation strategy called JCO, which generates semantically equivalent and distinct augmentations using large generative models, creating both positive and negative view pairs that enhance the model's ability to learn nuanced visual semantics. Together, these components enable TULIP to outperform existing models in various vision language tasks.
Can you come up with a simple yet illustrative example to explain the inner workings of TULIP? Walk through one of the main algorithm steps with an example.
An illustrative example of TULIP's inner workings can be seen in its generative contrastive view augmentation process, specifically through the JCO method. For instance, consider an image of a cat sitting on a bench, paired with the caption, "A cat is sitting on a bench." TULIP generates positive views by slightly altering the image, such as rotating the camera angle, which maintains the same semantics but changes the visual representation. Simultaneously, it creates negative views by introducing a semantically distinct element, like adding a dog to the scene, which retains similar visual features but alters the overall meaning. This dual approach allows TULIP to learn nuanced visual details and spatial relationships by contrasting these generated views during training, enhancing its ability to understand fine-grained visual semantics. Thus, through this process, TULIP effectively unifies diverse perspectives of the same content, improving its performance on various vision language tasks.
What are the theoretical or practical benefits of using TULIP over existing CIT models? What specific metrics or benchmarks does it improve upon?
TULIP offers significant theoretical and practical benefits over existing contrastive image text, CIT, models by enhancing the encoding of fine-grained visual representations and improving spatial awareness through patch-level global and local multi-crop augmentations. It also incorporates a reconstruction objective that preserves high-frequency local visual details, often overlooked by traditional CIT methods. Practically, TULIP demonstrates superior performance across various benchmarks, achieving state-of-the-art results in zero-shot classification on datasets like ImageNet 1K, INAT 18, and CIFAR 100, as well as fine-grained recognition tasks on datasets such as RxRx1 and FMOW. Additionally, it excels in text-based image retrieval tasks on COCO and Flickr, and shows over 3x improvements on the MMVP benchmark for vision-centric tasks compared to existing CIT models. Notably, TULIP also outperforms existing models by up to 30% on the win-aground benchmark, showcasing its enhanced reasoning and perceptual skills.
How was TULIP validated or tested in the experiments? Describe the experimental design, datasets used for evaluation, and the metrics measured to demonstrate its effectiveness.
TULIP is validated through a comprehensive experimental design that evaluates its performance across various vision and vision language tasks. The model is tested on a diverse suite of datasets, including general-purpose zero-shot classification datasets like ImageNet 1K, INAT18, and CIFAR100, as well as fine-grained classification datasets such as RxRx1, FMOW, and infographics. Additionally, TULIP's capabilities are assessed in text-to-image and image-to-text retrieval tasks using COCO and Flickr datasets, and its robustness is evaluated as a visual encoder for LLAVA-style models on the MMVP and UMBench datasets. Metrics measured include zero-shot classification accuracy, retrieval performance, and reasoning skills, with TULIP demonstrating state-of-the-art results, including over 3x improvements on MMVP tasks and up to 30% better performance on the win-aground benchmark compared to existing CIT models. Overall, the experiments highlight TULIP's enhanced encoding of fine-grained visual representations and its effectiveness in both vision-centric and language-centric tasks.
What results were achieved with TULIP in comparison to other state-of-the-art models? Can you cite specific performance metrics or findings that highlight its improvements in downstream tasks?
TULIP demonstrated superior performance compared to existing state-of-the-art SOTO models across various benchmarks. Specifically, it outperformed models like CLIP and SigLIP in zero-shot classification tasks on datasets such as ImageNet 1K, INAT18, and CIFAR100, achieving new SOTO results. In fine-grained recognition and object detection tasks, TULIP also excelled, with improvements noted in the Blink benchmark, where it achieved up to a 12% relative improvement over SigLIP-trained baselines. Furthermore, TULIP showed remarkable performance in vision-centric tasks, yielding more than 3x improvements on the MMVP benchmark when used as a visual encoder for LLAVA-style models, without degrading performance on language-centric tasks. Additionally, in visio-linguistic compositional reasoning tasks, TULIP outperformed existing CIT models by up to 30% on the win-aground benchmark, marking a significant advancement in fine-grained visual understanding.